Hello everyone, welcome back to Linked Frequency. In this tutorial, we are going to learn about the complete Arduino Nano development board design using the easyEDA tool. This is the part 3 of episode 20 of Practice Project for PCB Designers. I am Vaibhav Sugandhi, passionate PCB designer and technology startup founder, helping you to design a complete Arduino Nano development board in this course. I hope you have watched and completed a schematic design according to the previous part. This is the third and final part of complete Arduino Nano development board design activity, wherein this one is going to show you how to design a PCB layout for the schematic and the diagram that you have created in a previous tutorials. Now let's start with the agenda. First thing is, we understood that this Arduino Nano development board is very compact and full of SMD components. Only connectors are a through-hole one. According to this, we did our datasheet analysis and a black box diagram analysis and a datasheet analysis, white diagram analysis, and also we did a morphological chart according to the requirement. Now we came to the conclusion that this is how the reference schematic looks like, and according to that, we have designed our schematic diagram. This is the schematic which we discussed in our previous tutorial, which is the second part of episode 20 of Practice Project for PCB Designer. Now the next part is to go to the layout and design a PCB layout as per the requirement and as per the IPC standard. First thing is, we'll get into the constraints or mechanical constraints for this design. As we are literally designing an Arduino Nano development board, it should be looking like an Arduino Nano development board. If you are designing something bigger than that or something completely different visibly, then it doesn't going to make sense for the design engineers. That's why we are going to consider the constraints given in the internet. First thing is, the entire board is going to be 43.2 mm. Why they have designed it exactly 43.2, I really don't know, but we'll make it as a 44 if it is required. But approximately it should be near to 43.2 or 44 is fine. And then this point to this point, the holes which are so-called mounting holes, they are exactly placed with the 40.64 mm. You have to manage it to be 40.64 mm only. You cannot make it a 40.7 mm, neither you cannot make it 40.6 mm. It's not recommended. Still you can do it, but it's not at all recommended. It's better to manage or maintain the industrial standard which is already exists in the market. Thereafter, we have a pitch between this point to this point or this hole to this hole, which is 15.24 mm, and the entire width of the PCB is going to be 18 mm. These are the mechanical constraint, and the drill hole, whatever we are having here, which are so-called mounting hole, will be 1.8 mm actually. I really do not understand why they are using 1.8 mm here, because generally we use a 2 mm or maybe a 3 mm actually. Maybe there is a certain constraint, that's why they are using 1.8 is what I assume. So we are going to follow the same thing as well. If you want, you can make it 2 mm, not a big deal, but yeah, 1.8 mm is recommended. And we already know that these jumpers, whatever we have here, jumping wires or jumper headers we call them, they are already having a 2.54 mm pitch between them. So placing them exactly middle of this PCB is a challenging one, which we are going to do in this particular tutorial. And placement of the USB on the board edge, LEDs on the middle, reset button beside them. So all these things are the visually known constraints which explicitly not necessary to be given to the participants. Why? Because when we look at the Arduino Nano development board, we can see them, all these components are placed in a very proper way. And we must understand there are components placed beneath of this PCB as well. Means it is a double-sided 2-layer PCB designing. So we should go for that kind of a PCB layout design engineering. So now let's jump into the schematic. First thing what we need to do is we need to verify the footprint. I'll go to the USB and open the footprint manager. First thing, I'll go to the capacitor. First thing in this entire list is a capacitor, which is 0402, which is correct one, and 4.7 electrolytic capacitor, tantalum electrolytic actually, so that's one is SMD, good one, and 22 picofarad, 100 nanofarad, all these things are SMD, looks good to me. While selecting the component only, I have selected them very properly as much as possible from my side. So even this the Schottky diode, what we have, that Schottky diode is also having a SOD 123 package, which is all about SMD. So it's a good one actually. Headers are through hole. Those are the only thing which are through hole in this entire circuit. LEDs are 0603 package, good one. And push button is also SMD one, which is absolutely good one, and it resembles the exact diagram on the Arduino Nano development board, which is available on the internet right now. You can see here, right? So that's why I'll keep it like that only. And then the resistors are 0402, all are 0402. That is a good one actually. 0603 is also good one to select, but not recommended because size is very small and we cannot manage to keep all the components with the 0603 only. Okay, so and then we have a main controller IC, which is a TQFP32 package, and then another one is USB to UART IC, which is all about SOIC 16, and then 1117 regulator, which is all SOT89, a small line package, small outline package, and then we have a USB, which is again SMD1. Crystal oscillator, this one is not a correct footprint according to the Arduino Nano development board. You can see here it is a very small one and it is not having any vertical length like this. That's why I have searched for the crystal oscillator and went into this LCSC option, because I have not designed any such packages. So when I went to LCSC, you can see here there are so many crystal oscillators are visible to us. I think there is a 3-pin crystal oscillator here, which is not correct one. Let's go for the 4, 5th. I think this one. No, not that one. Maybe I have messed it somewhere. Let me search for it. 4-pin not recommended, 2-pin is also not recommended. Let's scroll a little bit. 3-pin one, which I literally saw it just yes, here it is actually. It's very difficult to identify a specific footprint without a specific part number. We don't have a specific part number for this crystal oscillator. That's why we are struggling to find a specific footprint. In fact, that is not recommended. However, I'm going with that because it's a practice project, and I'll select both the crystal oscillators, 16 megahertz, 16 megahertz, and I'll click on this particular footprint, whichever we just now selected, this one, and I'll double click on them. So you can see here those footprints are updated to both the components at a time. This is the shortcut actually, and other than that we don't have any other components. So all these components footprint verification is completed. This is the first step actually. Now we'll go to the design and click on the convert schematic to PCB. Now I'll check all the nets. As I already discussed about this point in our previous tutorial, which is a schematic design tutorial, you can see here RxD and D1 are having a conflict. It is a warning, it is not an error actually, but still we can go ahead with this. However, right now I'm interested to discuss about this. As we already discussed, RxD and D1, both net name are given to the single net, which is not at all possible according to the electrical standard. But however, we are just hijacking that particular standard and going ahead. So I'll go to the convert to schematic once again. Now I will click on the no, keep going, because we want to override that particular warning. Now when we come to the PCB layout, a new PCB wizard will visible to us. In the board outline, we will select a rectangular one, which we want as always. So I'll make a X0, Y0, and width is going to be 18 mm, or maybe I think I'll treat this as a width and this as a height actually. Is it available here? Yeah, height is available. Height is going to be 18, width is going to be 44 mm. I'll consider a 44 mm, and this one is going to be 18 mm. All right, all these components visible to you. I'll just take it all this side, and these little resistors also. All right, this is this looks really complex and very challenging for a PCB designer, because all these components has to be fit into this small size PCB. That is where you become a PCB designer actually. That's how the PCB designers are really challenged when they are designing something like this. Now I'll start with the first constraint, that is all about the placement of these drill holes. I'll make them a 2 mm or I'll make them a 1.8 mm. That would be more better, I feel actually. And they are placed exactly with a 40.64 mm distance from this point to this point. I believe that the difference between these two is going to be the difference of the board edge actually. So how to compute that? Use a calculator. So when you open a calculator, you know that 44 minus 40.64 is going to be 3.36, divided by 2 is going to be 1.68. So this is 1.68 mm is the distance from x-axis actually. So 1.68 is going to be the distance from this point to this point is 1.68, and the same one here also it goes. What about the height actually? Height is computed by the difference between these two. 2. So I'll just use a calculator once again. 18 minus 15.24. So it's going to be a 2.76 divided by 2 is going to be 1.38. A strange numbers, but yeah, that is how the industrial PCB is having. So I'll just follow that actually. What is that? What was that? 1.38. So minus 1.38. This looks a little weird to me because I have taken the large board size. Point difference in 0.8 actually. So that's why we have a 0.4 difference here. That's okay. It doesn't make a difference to me at this point of time. So I'll place one more drill hole here, one more here, and one more here. Let's bring those coordinates right to us. So first thing here is going to be a large number. So what is that large number? This one is 1.38. So minus 1.38, and this one is 1.68. So total is 44 minus 1.68 is going to be 42.32. So 42.32 is going to be like this, and here also we'll make sure that it is 42.32. Yeah, 42.32, and this one is going to be 1.68, right? Yeah, 1.68. So 1.68, and then we'll be having this pitch also. So we'll check about that as well. So total one is 18, and whatever we are placing here is a 1.38. So 18 minus 1.38. 18 minus 1.38 is going to be 16.62. So minus 16.62 is the right one, and here also it's going to be a minus 16.62. So this is how our constraints are set actually. Now board constraint, board edge is set, and also drill holes are set. I selected all of them and I locked them actually because they are standard. Now if you try to move them, they'll never move actually. That is what we want. And thereafter we will be having two headers here. One header is going to sit somewhere here, and another header is going to sit somewhere here. Which one sits where? I think we'll discuss it and decide it in a later stage. But right now I'll remove the display name. A prefix necessarily need not to be displayed because it will consume a space for us. And then we have a 15th one, so mid one is going to be a normal one. Now placing this particular thing in the middle, I think we'll check actually where D13 is here, so D12 is here. I think I kind of believe it's going to be like this actually. Why? Because D13 usually comes this side, so let's make it here. Okay, I'll just keep it like this, and now I'll select this particular header or the top side header, and we'll calculate. 44 divided by 2 is going to be at 22. So this mid one should be at 22. X location is going to be 22, and height wise it is going to be, I think its total width is somewhere around 2.54. No, not 2.54. It is pitch actually. So let's try randomizing it. 1.5. I think 1.5 looks good to me because 1.5 is having a good placement here. So I just prefer to go with a 1.5 at this point of time. So width is going to be at X location is going to be 22 for the beneath one or the bottom side one, and then Y location is going to be 18 minus 1.5 is going to be 16.5. So 16 minus 16.5. This is how you have placed your both the connectors. I'll select both of them and I'll lock them permanently. So now you can see that this cannot be moved, this cannot be moved, this cannot be moved, this cannot be moved, nothing can be moved in this. I'll just see if it is possible to lock the board also. Yeah, board edge is also can be locked. So once I lock the board edge, you can see that it cannot be edited further. This is how the mechanical constraints are set in the PCB designing. This is now standard. We cannot move this and we don't want to move it by accidentally or by intentionally. Both ways we don't want to move that. That's why I have set it permanently. Now I'll go back to my circuit and I'll see that this is a place where USB sits. So let's bring the USB in the system. Here we have a USB and I will rotate it like this and I will place it somewhere here. How to place it in the middle again? So once we select it, actually you can see it is having a anchor here, which is the origin of this component here. Actually it is set to be middle. Always it will be middle. So most of the time based on again footprint designer and all, but right now most of the standard designs are having a professional designs are having a midpoint as the set point for the rotation or the placement of the component. So I'll keep this component here, and I know total width is 18 and divided by 2 is going to be a -9. So I'll just hit the -9. this is exactly at the middle right now. It's 100% sure it is at the middle according to the height actually. With respect to width, obviously it is at the board edge. Based on the board selection, I'm seeing that. If you still want, you can take it a little bit outside like this so that it will be exposed for the programming. But make sure that again you make it a -9 in the Y location. Once you are done with that, select that component and lock it again. This is how you start setting the constraint for yourself. And I'll select it and I'll remove the display prefix also because we don't want it. Thereafter, what we have a microcontroller IC and all these components. I think by using this image, you can start placing them as per the standard. Let's do it together in the fast forward way. Alright, now you can see here, according to the IPC standard and according to the electrical standards of development board design, we have placed the components as per the industrial product available on the internet right now. I think there are some minute changes which we have done in this particular project. One is not adding these SPI connectors actually. You can see here, these SPI connectors, a 6-pin header is necessary for connecting a SPI protocol based peripherals directly to the board without using these normal GPIs. In fact, internally these normal GPIs only connected to these SPIs. They are not separate or they are not special things. They are just a utilization of these SPIs in a direct fashion, SPI fashion. However, we have not added that because we felt it is not necessary for us at this point of time. And we added a couple of extra capacitors, as you know, crystal oscillator requires the capacitance, a body capacitance to be managed. That's why we added a couple of things. But in our design, those things are not adding much of a difference to the entire design. That's why we kept it. As we removed these header, we got a good space over there. So utilizing that space with the USB to UART converter is what I felt is the right one at this point of time. But once we start doing a routing activity, probably we may feel it is not a good one and we may bring it back to this place as per the requirement. Again, we are still open. We have locked the USB, we have locked the mounting holes, we have locked the connectors, but we have not locked any one of these components because those components will play around or we will move them as per the requirement while we are doing a routing activity. Majorly, a concept of how to place the components on this small PCB is completed. If you look at the photo view, this is how it looks like. It's a bottom view, and if you look at the top side, this is how it looks actually. Looks very constrained and very compact design at this point of time, and maybe for those who are doing this kind of a circuit for the first time, it looks extremely complex to you at this point of time. But do remember, this is how the PCB designing looks like, and we are still at the 2-layer PCB designing, a 2-sided PCB designing. If you go to the industry with IoT devices and smart edge computing devices, they are going to be a 4-layer, 6-layer, 8-layer, up to 32-layer, and on that time you are going to deal with more and more components in small size. A smartwatch, imagine a smartwatch actually, how complex it is. This Arduino Nano development board has hardly a 40 components, probably not more than 30-35 components probably. I think we'll check it here in our schematic. If you go to the design engineering, next here 32 components. We have only 32 components in this PCB, but we are feeling very complicated. But trust me, when you go to the higher design, more than 60 to 70 components can be managed in this small area. Again, depends on the size of the component, package of the component, how compact they are, and how to place them, all that thing. Let's come back to the topic. We have placed the components properly. Now it is a time for routing activity, which takes a little extra time. Why? Because it is completely SMD and a lot of complex things are there. It takes a lot of brainer activity. Let's try to do it as fast as possible. Alright, after waiting a lot of time and doing a very brainer work, we completed up to 30 nets in this entire PCB. I'm very sure this is going to be a very complex one, and it's not possible in just one video. That's why we divided the entire project into 3 videos, 3 parts, but still these 3 parts are also not sufficient for such a complex design. One important thing I just wanted to tell you and close this video so that you can practice by yourself. The one important thing is, look at the entire design right now. I have changed the placement of certain components according to my wish, according to my knowledge, or according to my comfort, you can say. By doing so, we ended up in such a complex phenomena where we are not able to think through how to complete this routing activity. For example, you can see here, this is a D4 pin actually. So D4 pin supposed to be connected to this one, and a net is visible to you, a rat lines is visible to you. But look at this. I mean, we don't have a possibility to go with a bottom copper. We can't add a wire here because there is a track, and we don't have an option for the top side also, because where do you take it actually? In the back side we have a VCC connection, at the front side we have a crystal oscillator. So it's very complicated to think through and understand how to take a track for D4 connection. However, it is possible. I'm not saying it is not possible, but it is very difficult. But this difficulty can be reduced to a great extent if you do a proper placement of these components according to the standards and according to the design constraints in your mind. When I started placing these components, I thought of aesthetics and I thought of copying the existing module directly, but still I have not copied it completely, as I mentioned in the the part, actually the beginning part of this video. I have changed this header and I placed the USB to UART converter at that place, and these connectors also, where there is a RxD TXD ground, V in ground, and opposite to that there is a RxD TXD. But in our case it is the same one actually. Even V in is also here and RxD TXD are also here. But the important part is the USB side, it is different actually. It is opposite to the USB side. Are you able to notice the difference here? This RxD and TXD is here and V in is here, where there is a header. The USB is opposite side to that, and USB is having some other D12 and D13 pin connection. In our design, what we did is D12, D13 pin is this side, and we placed our USB on this side, because of which we are not able to figure out these remaining 12 connections. Ground is a one which we will do it by pouring the ground layer on the copper and all, but using too many wires are also not recommended, and placing these components in a wrong way will bring you to this kind of a complexity. Yet you can solve that problem by doing a proper brainstorming or finding a solution to this particular scenario. However, I just want you to remember, this is a complex methodology. This is where the real PCB designing starts. Until here, whatever you did, it is all about practice. That's why this entire tutorial series is so called Practice Project for PCB Designer. Now the real practice is going to happen, or now the real PCB designing starts. This is where the PCB designing comes into the picture. This is where the brain, or there is the logical thinking, analytical thinking, problem solving skills, all those parameters comes into the picture for the PCB designer. I will complete this entire PCB in another few hours or maybe something like that, and I will post final video maybe in the next part of this tutorial if it is possible. But till here, I believe you got to know that how exactly this PCB looks like and how to complete the routing activity. I believe that you are going to complete it by yourself by completing this entire routing, and then if it is possible, comment down in the comment section how was your experience doing such a complex circuit for the first time. It is going to be very valuable and a great learning in this entire process. Do let me know your learning experience in comment section, and if you get any questions regarding this, feel free to ask me. I will try to answer my level best as much as possible early. Okay, so this is all about the designing the Arduino Nano development board by yourself. Complete Arduino Nano development board. And if you have funds and if you are very much interested, you can literally manufacture this entire PCB and assemble the components with a bit of help of an experienced person. Literally, you can use that product for your entire project activity here and after. Thank you so much for watching this entire tutorial, guys. 3 parts. First part is all about design thinking or the designing the entire system. Second part is all about the schematic, and the third part is this one, the PCB layout. Though it is not complete, but I believe you will do it by yourself because it takes a lot of time for me to complete it here. In this video, we don't have sufficient time. That's why. And I also believe that you understood the concept of designing a development board, concept of SMDs, concept of 2-layer design and a 2-sided design. And if you get any questions, do let me know in the comment section. Thank you so much for watching. See you again in the next video. Until then, consider subscribing to our channel Linked Frequency. Share this video with someone who may need it, and tune yourself to make a difference.